All right. Um, so today we're going to be talking about Thevenin's theorem and Norton's theorem. But before we do that, I want to mention a couple of things here. So I've been made aware of at least one mistake on at least one of the exams. So I'm going to be going back through the exams over the next couple of days and just trying to make sure that, you know, trying to find any more mistakes that might have occurred. It was my first time putting a test on Canvas and all of that kind of stuff. I just want to make sure that you guys' grades and all of that kind of stuff are accurate. Um, I was a little bit surprised to see that the highest score on any of the versions of the exams was an 88.5. So that leads me to believe that there's likely some mistakes on my part. So I would not be surprised if some of your grades changed for the better over the next couple of days as I get all this kind of stuff sorted out. I understand a lot of you are concerned about your tests, all that kind of stuff. Perfectly okay. Uh, Give me a couple of days to get everything sorted out and make sure that everything is fixed, and then we'll go from there. All right. So, Thevenin's theorem. So Thevenin's theorem states that, any linear two-terminal electrical network can be replaced at the terminals by an equivalent voltage source I'm going to label this voltage as VTH, and I'm going to refer to that as the Thevenin voltage. In series with an equivalent resistance, RTH, which I'm going to refer to as the Thevenin resistance. Okay. So before we talk about how we determine the value of the Thevenin voltage and the value of the Thevenin resistance, let's take a moment to effectively see what this thing tells us, okay? So Thevenin's theorem says that any linear two-terminal electrical network can be replaced by a voltage source in series with a resistance. So effectively, Thevenin's theorem just tells us that we can replace a linear network with an electrically equivalent practical voltage source, okay? So this is very similar to what we were doing right before you guys took your test. We're just looking at it from a slightly different perspective, okay? So now let's talk about the rules for determining the Thevenin equivalent circuit of a particular network or portion of a network, okay? So first, let's talk about the voltage, okay? The equivalent voltage V Thevenin is the open circuit voltage measured across the terminals of the live network, where a live network simply means that all of our independent sources are turned on. Okay? The equivalent resistance R Thevenin is the resistance seen looking into the terminals of the dead network, where a dead network simply means that all of our independent sources are turned off. And we do this using the exact same rules as superposition, meaning to turn a voltage source off, we replace it with a short circuit, and to turn a current source off, we'll replace it with an open circuit. So let's put Thevenin's theorem into practice by determining the Thevenin equivalent circuit for a particular network. Okay, and there are really two different ways that we can, or I say two different ways. There are two different situations that we might have, and we'll talk about both of them here. Okay, so let's call this guy right here example number one. Okay, and we want to find the Thevenin equivalent circuit seen by the 1 ohm resistor. So we have the following circuit. Here we have a 4-volt source. Here's a 9 ohm resistor. There's a 3-volt source. A 10 ohm resistor. Another 10 ohm resistor. 5 ohm resistor. A third 10 ohm resistor. And finally, the 1 ohm resistor mentioned in the problem statement. Okay. So when we're asked to find the Thevenin equivalent circuit seen by a particular circuit element, what we are going to have to do is to take that circuit element out, and that's going to leave behind a pair of terminals that are mentioned in our definition for our Thevenin equivalent voltage and our Thevenin equivalent resistance. Okay, so if we want to find VTH, let's talk about what that is going to entail. So I'm going to redraw our circuit, and I'm going to leave the 1 ohm resistor out. Okay. So effectively, we're replacing the 1 ohm resistor with an open circuit. Sorry, it's just taking me a moment to redraw this. I typically tend to put a set of terminals where the resistor or element of interest was to let me know, hey, this is what I'm looking at. And so I've drawn these terminals here, and our Thevenin voltage is defined as the open circuit voltage seen across this set of terminals. Now, I'm going to choose to represent that voltage with positive polarity on top. Usually in your exams, homeworks, all of that kind of good stuff, you will be explicitly told where to put the positive polarity reference for any circuits that you're finding the Thevenin equivalent of. Okay, so that's why I just arbitrarily chose top here. In the grand scheme of things, it's not going to matter much, and we'll sort out all the rules. But I just want to let you know that you will have guidance where to put the positive polarity terminal in any problems that you're asked to work. All right, so how could we go about solving for the voltage VTH for this particular circuit? Would anybody care to volunteer a suggestion?
Mesh analysis?
Mesh analysis, okay. So there isn't anything remotely wrong with that suggestion. It is not the way that I would do it, but we'll do that first, and then I'll talk about how I might approach it and why I made a different decision, okay? So I'm going to identify my meshes, and I'm going to go ahead and label them at the same time. So this is going to be my mesh current A, and then here I'm going to have a mesh current B. There will not be a mesh current flowing in the bottom right-hand kind of box thing because we don't have a closed path. So we know that any current that's circulating around there has to be zero because there's no closed current carrying path. Okay. So applying mesh, we have a fairly straightforward circuit here where we don't have any current sources or anything like that to worry about. So realistically, we're just going to have a KVL equation around mesh A, a KVL equation around mesh B, and then we'll go from there. Okay. So KVL at mesh A should look like this. So we're going to have negative 4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. And KVL at mesh B is going to look like 9 ohms times IB minus IA plus, so I've got 10 ohms, 5 ohms, and a 10 ohms, and they're all in series. So I'm just going to add those together and say 25 ohms times IB is equal to 0. And then I'm going to solve that system. So give me just a moment to do that. So using my trusty TI-36, it's a 2x2 system. My coefficient for IA in my first equation is positive 9. My coefficient for IB in my first equation is negative 9. And then I'm going to have plus 4 minus 3, so that looks just like 1 as my constant term. And my second equation, my coefficient for IA is negative 9. My coefficient for IB is 9 plus 25. And my constant term is 0. And so when I solved this, I got currents of 34 over 225 amps and 1 over 25 amps. Did anyone else get something similar?
I got the same thing.
All right. So now that we have these mesh currents, how can we use that to solve for the voltage VTH?
We can analyze at one of the terminals of VTH. with the currents that we have?
So what do you mean by we can analyze? Like, what specific analysis technique are you thinking of?
I was thinking about just continuing with mesh analysis and thinking as if we had like IB flowing through the 5 ohm and the 10 ohm into the positive node on VTH.
So, um, I'm not 100% sure that I'm following there. I do want to be clear, and I think we might be thinking the same thing, but speaking about it differently. Um, there is no current. Let me put a label here. Like, we know for sure that there is no current that's going to branch off of IB and flow down through this particular path because it contains an open circuit. So what I would suggest that we would do is, now that we have these mesh currents, we could write a Kirchhoff's voltage law equation. Okay. So what I'm going to do is I'm effectively going to write a KVL equation around this path. So let me just write here KVL at purple. And so when I apply Kirchhoff's voltage law here, I can see that my voltage rise of VTH is equal to the sum of my voltage drops. So that's going to be 10 ohms times IB plus 3 volts plus, and I'm doing this explicitly here, 10 ohms times 0 amps. For me to recognize that there is definitely not going to be a voltage drop across this 10 ohm resistor down here on the bottom, because it's not part of a closed current carrying path. So when I substitute in my value for IB, so 10 over 25 plus 3, I wound up getting 3.4 volts. So any questions about that particular analysis in order to get our Thevenin voltage VTH? All right. So I mentioned a couple of moments ago that this is not how I would have chosen to analyze this circuit. So what I'm going to do is I'm going to make a copy of this really quickly. And I'm going to talk about how I would do it. And the short answer is that I would choose to use nodal analysis. I can leave my observation that a current of 0 amps is going to flow down through there, and therefore a voltage drop of 0 volts is going to occur across the 10 ohm resistor. But let's see how this is going to shake out using nodal. Okay. So I'm going to identify my nodes just really quickly here. So you may be looking like, let's see, I have 1, 2, 3, 4, 5, 6 nodes, but I still firmly believe that nodal analysis is actually the better tool to use here. And so you may be thinking to yourself, what the heck is Dr. Hartman smoking today? Which is a fair thing to think about. But let's put it in context, right? So we know that if I choose ground to be the bottom node so that it's touching both voltage sources, I know that the nodal voltage at our red node is just 4 volts. And I know the nodal voltage at the blue node, or the dark blue node, is 3 volts. I also know that since there's no voltage drop across the 10 ohm resistor on the bottom right, that the light blue node and the light green node are effectively the same node because they're both at ground. So realistically, I only have an unknown voltage here. Let's call this one, for lack of a better term, Vx, and an unknown voltage here, Vy. All of my other voltages are known quantities, right? We know that this node is at 4 volts. We know that this node is at 3 volts. And we know that this node is at 0 volts. So I'm going to have a 2 equation, 2 unknown system. So if I apply KCL at node X, I wind up getting Vx minus 4 volts over 10 ohms plus Vx minus Vy over 5 ohms is equal to 0. I apply KCL here at node Y, and I will have Vy minus Vx over 5 ohms plus Vy minus 3 volts over 10 ohms is equal to 0. And now I'm going to solve for Vx and Vy really quickly. So once again, I have a 2x2 system. My coefficient for Vx in my first equation is 1/10 plus 1/5. My coefficient for Vy in my first equation is negative 1/5, and my constant term is 4/10. In my second equation, my coefficient for Vx is negative 1/5. My coefficient for Vy is 1/5 plus 1/10. And my constant term is positive 3/10. And when I solve this system, I get Vx to be 3.6 volts and Vy to be 3.4 volts. Okay. Now, Vy is nothing more than my Thevenin voltage in this case, because the positive polarity terminal of VTH is at node Y, and the negative polarity terminal is effectively at ground. So I feel that using nodal analysis here is actually a little bit easier than using mesh, particularly because we solved the same size of system, but nodal analysis gives us voltages, and we were looking for a voltage. So that's why I felt that nodal was a little bit better method to use for this particular problem. Any questions on how I applied nodal analysis to this? All right. So now,
Sorry, I had a question, Dr. Hartman.
sure.
So it would be about polarity flipping. So the negative polarity terminal of VTH being on the top,
Mm-hmm.
that would just make our it would be Vy equals negative VTH.
Exactly right. All right, so when we're finding our Thevenin equivalent resistance, we need to, once again, take out our element of interest, so the 1 ohm resistor, but we need to be looking at a dead network. So For our dead network representation, our 4-volt source needs to be turned off. So I'm replacing it with a short circuit. Then we have our 9 ohm resistor here. Our 3-volt source is also turned off, so I'm replacing it with a short circuit. Here's a 10 ohm resistor, a 5 ohm resistor, a 10 ohm resistor, another 10 ohm resistor, and then here are the terminals that are left behind when I took my 1 ohm resistor out. Okay. We are going to be looking into the open circuited terminals of our dead network and trying to find this resistance RTH. And so whenever we just have a circuit or system that contains only independent sources and resistors, this just becomes a resistor combination problem. On Wednesday's class meetings, we'll talk about what happens when there are dependent sources involved, but we're not ready for that quite yet. Okay? So I can't see just from the jump what the equivalent resistance of this thing is. So I'm going to identify my nodes. So I've got this big red node here. I've got this blue node, this green node, and let's do this purple node. What does it mean that the 9 ohm resistor is effectively touching the same node on both sides?
It gets bypassed.
Exactly right. So it's shorted out. So the 9 ohm resistor is not going to contribute anything at all. So let's call this node A, this B, this C, and the red node D. And I'm going to put A over here on the left-hand side and B over here on the right-hand side. So to go from A to B, the simplest path would be to go from A to D to B. So let's stick D here in the middle. From A to D is the 10 ohm resistor. This one right here. From D to B is this 10 ohm resistor. And then we have an alternate path to go from A to D that goes through node C. So to go from A to C is this 5 ohm resistor. And then from C to D is this 10 ohm resistor up top. So it looks like our Thevenin equivalent resistance is going to be 10 ohms in series with the parallel combination of 10 and 15. So I'm going to put that in my calculator really quick. It's going to look like 10 plus 10 times 15 over 10 plus 15. And that comes out to be 16 ohms. So let's recap some things here really quickly, okay? Whenever we're finding the Thevenin equivalent resistance with respect to a particular circuit element, we have to take that circuit element out of the system because we don't want it influencing our measurements or calculations effectively, okay? So we took it out, leaving behind an open circuited set of terminals that we used to find the open circuit or Thevenin voltage in our first part. And then we also took it out and it left behind the set of terminals that we look into to find our Thevenin resistance as well. So let's shift gears really quickly. Actually, before we do that, let's talk about what we've done now. So we had our original circuit that looked something like this. And now we can say that this circuit that I'm drawing over here to the right is electrically equivalent, because our Thevenin equivalent circuit has to be electrically equivalent to our original network. Okay? So if we were trying to find the power delivered to the 1 ohm resistor or something like that, the Thevenin equivalent circuit would be the easier one to analyze, just specifically worried about the power. So this is something that you can actually use in practice. So let's say that you were trying to design a system and you wanted to deliver a particular amount of power to one of your elements, but you wanted to make sure that you didn't exceed its voltage rating, its current rating, or its power rating, or something like that. Instead of analyzing the system as a whole, if you just replace the system with its Thevenin equivalent and then only worry about what's going on with the element that you're interested in, it's much easier to figure out whether or not you're going to be able to meet those ratings and whether or not you're going to burn out your component. So that's where Thevenin equivalent circuits are used in practice very regularly in designing complicated systems. Just making sure that you're not going to exceed any of the specifications for critical or expensive circuit elements. All right.
Dr. Hartman,
Sure.
is that voltage supposed to be 3.4 volts or 3.6 volts?
Let me scroll back up. I may have messed that up. 3.4 volts. I apologize for that. Thank you. So it should definitely be the Thevenin equivalent voltage there. Thank you for catching that mistake. Okay. So let's look at a second example real quick. And so in this one, we're going to look at the second case. Okay, so our first case was we were finding the Thevenin equivalent circuit with respect to a particular circuit element. Now we're going to find the Thevenin equivalent circuit with respect to a set of terminals. Okay? So whenever we're finding the Thevenin equivalent circuit with respect to a set of terminals, we don't have a circuit element to take out anymore. So we can effectively just apply everything directly. Okay? So our circuit of interest is this guy right here. We have a 3-volt source in series with a 2 kilo ohm resistor. Here we're going to have a 7 milliamp source direction down in parallel with a 5 kilo ohm resistor. And then over here to the right, we have a 1 kilo ohm resistor and then an open circuited set of terminals. I'm just going to call this terminal A and this terminal B. And I'm asking us explicitly to find the Thevenin equivalent circuit seen between terminals A and B. And let's assume positive polarity will be on top for our Thevenin equivalent voltage. So to find VTH, we were literally just going to redraw our circuit as is, make no modifications whatsoever, except to say that the voltage drop between terminals A and B is our Thevenin voltage. So how do you guys suggest that we go about solving for this Thevenin voltage VTH?
We could do nodal analysis.
So we definitely could. Did somebody else have a suggestion?
Would
Source
it be,
transformation?
yeah, would it be too complicated to do the source transformation?
So which source transformation are you referring to? Because I see two practical sources.
The voltage with the 3 volts with a 2 kilo ohm converted to a current source.
So I'm going to choose to ignore your suggestion, and I'm going to do a source transformation on the other practical source. And you might see why. Actually, hold on. No, that'll work. Sorry, I got ahead of myself there. Okay. So if we were to do a source transformation there, that's fine. So we would have, let's see, 3 volts divided by 2 kilo ohms is going to give me 1.5 milliamps up. Here's my 2 kilo ohm resistor. Here's my 7 milliamps down. Here's my 5 kilo ohm resistor. 1 kilo ohm resistor. So I believe I have done this source transformation correctly. Anybody have any problems with that? All right, so now that we've done that source transformation, how do we find that voltage?
We'll combine current sources, convert back into a voltage source, and then we can probably solve from there.
So you're putting a little too much effort into things. So let me explain what I mean by that very specifically. What is the voltage drop across this 1 kilo ohm resistor right here?
Zero.
0. Why is it 0?
There's no current flowing through it. It's an open circuit.
Exactly right. So that means that the Thevenin voltage is actually just the voltage drop across all of these things in parallel. So your suggestion of combining our current sources together, I'm 100% on board with, but past that point, you're just doing extra work because I believe very fundamentally that we can just use Ohm's law, right? So our Thevenin voltage, I believe, would be 1.5 milliamps minus 7 milliamps. That's me just combining those two current sources together in parallel. There's a minus sign there because they are in opposite directions. And I'm choosing to give the 1.5 milliamp the plus sign effectively, because I want the resultant current to be the one that's flowing up into the positive polarity terminal. Now I'm going to have 2 kiloohms times 5 kiloohms over 2 kiloohms plus 5 kiloohms. And I'm going to throw this into my calculator. So 1.5 minus 7 times 10 over 7. I got negative 7.857 and some change volts. A couple of minutes ago, someone suggested that we do this using nodal analysis. So let's do that really quickly and just make sure that we get the same answer. Okay. So I'm just making a copy of this thing right here. We're just going to try it a different way, just to make sure that we understand what's going on. So to the person who suggested nodal analysis, where do you think we should put our ground? Okay, well, I'm going to choose to put ground on the bottommost node, which happens to be the negative polarity terminal of our Thevenin voltage. I believe we can very easily understand that the voltage drop across our 5 kiloohm resistor is the same thing as our Thevenin voltage, because once again, there's still no voltage drop across the 1 kiloohm resistor. So Kirchhoff's voltage law tells us that the voltage drop across the 5K resistor is VTH. And if we apply nodal analysis, let's just call this node A, we would have VA minus 3 volts over 2 kiloohms plus 7 milliamps plus VA over 5 kiloohms is equal to 0. One equation, one unknown system. Let's solve it for VA really quickly. So I have, let's see, x minus 3 over 2,000 plus 0.007 plus x over 5,000 is equal to 0. Solving for VA, I get negative 7.857 volts. And very obviously, I hope VA is the same thing as VTH, because the positive polarity terminal of VA, the positive polarity terminal of VTH is at node A, and the negative polarity terminal of VTH is at ground. So we got the exact same answer either way, which is great. One of the things that I like the most about using Thevenin and Norton equivalent circuits as a circuit analysis technique is that it really doesn't matter what method we use to get our Thevenin voltage. So if you're comfortable doing nodal analysis, that's great. If you're comfortable doing mesh analysis, that's great. If you're comfortable doing source transformations, that's great. They all get you to the exact same answer. All right. Now let's work on our Thevenin equivalent resistance. So for our Thevenin equivalent resistance, we need to turn off our independent sources. So that means our 3 volt source is replaced with a short circuit. Here's our 2 kilo ohm resistor. Our 7 milliamp source is going to be replaced by an open circuit, so I'm just not drawing it. Our 5 kilo ohm resistor would go over here. And so we're looking in here and trying to find RTH. So what do we see looking into those open circuited terminals on the right?
1 kilo ohm plus the parallel of 5 and 2.
Exactly right. So let's see. 1 plus 10 over 7 is, let's see, 17 over 7 kilo ohms. Yep. Okay. So just to recap here, whenever we're finding the Thevenin equivalent circuit with respect to a set of terminals, we don't need to take any circuit elements out of the system, okay? All right, so any questions about Thevenin equivalent circuits before we move along to Norton equivalent circuits?
I had a theoretical question.
Sure.
So let's say you completed the circuit between those two terminals.
Mm-hmm.
And let's say we had a terminal at the intersection point above the 5 kilo ohm resistor and below it. And we were asked to find the Thevenin equivalent between those two terminals. How would you break up this circuit?
So so I believe you emailed me about homework 9 problem 4.
Yeah, I don't know if you want to do it after class. It's that one basically.
Yeah, so I was fully intending on working that problem specifically with you after I wrapped up the lecture. So
Yes,
can
sir.
we hold off on that one really quickly?
Yes, sir, of course.
Okay, because I thought that's what you were leaning towards if I remember that problem correctly. Okay, any other questions about Thevenin equivalent circuits before we move on to Norton? All right, so Norton's theorem is very, very similar to Thevenin's theorem. Okay. So Norton's theorem states that any linear two-terminal electrical network can be replaced at the terminals by an equivalent current source INO, or which I'm going to call the Norton current, in parallel with an equivalent resistance. RNO, which I'm going to call the Norton resistance. Okay. So Thevenin's theorem effectively tells us that we can replace a linear two-terminal network with a practical voltage source. Norton's theorem tells us we can replace that same two-terminal electrical network with a practical current source. So let's talk about how our Norton current and our Norton resistance are defined. Okay, so the equivalent current I Norton is the short circuit current measured through the short circuited terminals of the live network and the equivalent resistance R Norton is the resistance seen between the terminals of the dead network. So the definition for the Norton resistance is literally the exact same thing as the definition for our Thevenin resistance. So you will never hear me refer to a Norton resistance again. I will always simply refer to Thevenin resistance, whether I'm dealing with a Norton equivalent circuit or a Thevenin equivalent circuit, because it literally represents the exact same thing. So let's put this into practice by looking at the two examples that we already worked, but now we're going to talk about how we find the Norton current for each of those. Okay. So example number 1 revisited. Let's talk specifically about how we're going to find I Norton. Okay. So when we were finding the Thevenin equivalent, we replaced the 1 ohm resistor with an open circuit. Now we're told very specifically that we should replace the 1 ohm resistor with a short circuit. And then our goal is to simply find the current that's flowing through that short circuit. So if I replace the 1 ohm resistor with a short circuit, my system is going to look something like this. And I'm going to choose to put my Norton current as flowing down. So realistically, I want to make sure that my Norton current is flowing into where the positive polarity terminal of my Thevenin voltage was. Otherwise, I might accidentally wind up with a negative resistance, which literally just means I got the direction wrong or the polarity of the voltage wrong. Doesn't really mean anything, but I'm going to try to make sure that doesn't happen. So how might we go about solving for this short circuit Norton current?
I'd probably say mesh.
Yeah, so mesh seems like a perfectly reasonable thing here. Not to say that we couldn't do it using another circuit analysis technique like nodal or whatever, but because we're trying to find a current, mesh seems like a pretty reasonable analysis tool here. So let's call this mesh current IA this mesh current IB. And because this bottom right-hand path is now closed, we will have a third mesh current IC that we have to worry about. So around mesh A, we are going to have -4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. Around mesh B, we are going to have 9 ohms times IB minus IA. Then I'm just going to add those 10 and 5 together because they are in series. So that's just going to look like 15 IB. And then lastly, I'm going to have 10 ohms times IB minus IC. Set that equal to 0. And now for KVL at mesh C, I'm going to have -3 volts plus 10 ohms IC minus IB plus 10 ohms IC is equal to 0. And let's solve this system. So going into system solver, we now have a 3 equation, 3 unknown system. So in my first equation, my coefficient for IA is +9. My coefficient for IB is -9. My coefficient for IC is 0. And my constant term is going to look like +1. In my second equation, my coefficient for IA is -9. My coefficient for IB is +9 plus 15 plus 10. My coefficient for IC is -10, and my constant term is 0. In my third equation, my coefficient for IA is 0. My coefficient for IB is -10, and my coefficient for IC is 10 plus 10, and my constant term is +3. When I solve this system, I get IA is 17 over 72. IB is 1/8. And IC is 17 over 80. Now that I know those 3 mesh currents, how do I find I Norton?
I Norton equals IC.
Exactly right. So I Norton, I wrote IC is equal to IC, my apologies. I Norton is exactly the same thing as IC, 100% correct. So we now know that a 17/80 amp current source in parallel with a 16 ohm resistor in parallel with a 1 ohm resistor is electrically equivalent as well, because our Norton equivalent circuit is just our Norton current in parallel with our Thevenin resistance that we found earlier. So as a quick tangent here, but it's not really much of a tangent, if our Thevenin equivalent circuit is equivalent to our original circuit and our Norton equivalent circuit is equivalent to our original circuit, then it stands to reason that our Thevenin equivalent circuit and our Norton equivalent circuit are equivalent to each other as well. So just as a thing here, our Thevenin equivalent circuit was 3.4 volts in series with 16 ohms. And then we had our 1 ohm resistor, our Norton equivalent circuit. We had I Norton in parallel with a 16 ohm resistor. And then here is our 1 ohm resistor. So hopefully we can all see and understand that our Thevenin equivalent circuit is just the source transformation of our Norton equivalent circuit and vice versa, right? So from that, we could say that our Thevenin voltage, VTH, is simply I Norton times our Thevenin resistance. Or we could say that our Norton equivalent circuit, or excuse me, Norton current is V Thevenin divided by R Thevenin. Or we could say that R Thevenin is equal to the ratio of V Thevenin to I Norton. And we can check that work here really easily. So if we take 3.4 and divide that by 16, I get 0.2125. Well, 17 over 80 is 0.2125, right? So realistically, if we can find two of those three quantities, we can always figure out what the third one is from these relationships. Or thinking about it in a slightly different perspective, if we can find all three of them, that's a way to make sure that we got everything right, because we can simply check to make sure that all of those relationships are maintained, which I just did. So any questions about finding the Norton current for this particular example? All right, so let's look at example number 2 and revisit that one. So I'm going to redraw our circuit. So we have a 3-volt source in series with a 2 kilo ohm resistor. Here's our 7 milliamp source. Here's our 5 kilo ohm resistor. Our 1 kilo ohm resistor. And now I short my terminals and I find the current flowing through my short. How might we go about doing this?
Mesh analysis.
So mesh analysis is definitely one way to do it. For those of you that were talking about the source transformation earlier, that would be a different way. So I think if we did a source transformation on the 3-volt source in series with a 2 kilo ohm resistor, we can then use current division to find I Norton. But mesh analysis is equally valid an option. So let's go ahead and do mesh, and that's what one of you guys actually suggested. So here's mesh current A, B, and C. All right, so I have a current source. So I have a current relationship equation that says 7 milliamps is equal to IA minus IB. Now I'm going to write my KVL equation, around supermesh AB. So that's going to look like negative 3 volts plus 2 kilo ohms IA plus 5 kilo ohms IB minus IC is equal to 0. And then we'll have 5 kilo ohms IC minus IB plus 1 kilo ohm IC is equal to 0. And we'll solve this system for IA, IB, and IC. All right, so resetting the memory on my calculator to get rid of that last system. All right, in our first equation, our coefficient for IA is 1, our coefficient for IB is -1, our coefficient for IC is 0, and our constant term is 7 milliamps or 0.007. In our second equation, our coefficient for IA is 2000, our coefficient for IB is 5000, our coefficient for IC is -5000, and our constant term is 3 volts. In our third equation, our coefficient for IA is 0, our coefficient for IB is -5000, and our coefficient for IC will be 5000 plus 1000, and our constant term is 0. Solving, I get 3.1176, so let's call it 3.118 milliamps, 3.882 milliamps, and 3.235 milliamps. So if we wanted to check our work, we could go back to where we found the Thevenin equivalent circuit for that guy. So that was, hold on. Oops, sorry, let me scroll back down. I missed a negative sign on this one and this one. My apologies for that. All right. So we went back to this part right here. I wanted to use a different color. I Norton should just be V Thevenin divided by R Thevenin. So that would be negative 7.857 volts divided by 17/7 kilo ohms. And I got negative 3.235 milliamps, which agrees with our direct analysis for computing our Norton current. So we must have done both parts correctly. Great. Okay, before we move along to the in-class assignment, any questions on Thevenin and Norton equivalent circuits? All right. So for this first problem here, we're asked to determine the Thevenin voltage, Norton current, and Thevenin resistance seen between terminals A and B. Assume the positive polarity for the Thevenin voltage is on top and the direction of the Norton current should be down. So which of the three quantities do you guys want to solve for first?
RTH.
RTH. Okay, so that's the easiest one, so seems reasonable to me. So to find our Thevenin equivalent resistance, we turn off our independent sources. So that means our 1.2 volt source is a short. We have a 49 ohm resistor, a 180 ohm resistor, a 96 ohm resistor, a 160 ohm resistor. Here's terminal A. Here's terminal B. We're looking in. What do we see?
+160 +96, +49 and 180 in parallel.
Exactly right. So I'm just going to throw that into my calculator really quickly. So 160 plus 96 plus 49 times 180 over 49 plus 180. 67,444 over 229, or crap. In decimal form, 294.51528. So let's just call it 515 ohms, which agrees with our expected answer. Okay, so what's next? Thevenin voltage or Norton current?
Voltage.
Thevenin voltage, okay. So now we need to be looking at our live network. So my 1.2 volt source should be on. .2 amps direction up. We were told to put the positive polarity terminal on top. So this is the circuit that we're analyzing, and we're trying to find VTH. So how might we go about this?
You
So
change the 1.2 volts into a current source, then source combination.
So
Do we just do nodal?
I personally would just do nodal analysis here. So the source combination thing here, like that would allow us to combine the 49 ohm resistance and the 180 ohm resistance, and then we will wind up doing another source transformation to be able to combine that equivalent resistance with the 96 ohm resistance, and then a source transformation back to be able to combine those current sources. So that's like 3 steps before we're even getting to a simplified circuit. Whereas with nodal analysis, we're just setting up the system once and calling it a day. So I would tend to use nodal analysis here. One thing that I want to point out, and you guys should start doing this regularly when you're doing these. So our Thevenin voltage is just going to be the voltage drop across the 0.2 amp current source, because we know there is no voltage drop across that 160 ohm resistance. Okay. The reason why I'm making that distinction is because it's going to make my nodal analysis system smaller, because I'm effectively saying that this node and this node are the same thing instead of having to write an entirely separate equation. So let's put ground down here on the bottom. Let's call this node A, this node B. And actually, let's do X and Y because we already have terminals A and B, and I don't want that to get confusing. My apologies there. So to me, this looks like Vx minus 1.2 volts divided by 49 ohms plus Vx over 180 ohms plus Vx minus Vy over 96 ohms is equal to 0. Then we would have Vy minus Vx over 96 ohms minus 0.2 amps is equal to 0. And we would solve this system for Vx and Vy. So let's do just that. If anybody has any questions about any of the terms in those nodal analysis equations, please let me know and I'll be happy to explain them. So my coefficient for Vx in the first equation is 1 over 49 plus 1 over 180 plus 1 over 96. My coefficient for Vy is negative 1 over 96, and my constant term will be 1.2 over 49. In my second equation, my coefficient for Vx is negative 1 over 96. My coefficient for Vy is positive 1 over 96, and my constant term is positive 0.2. When I solve that system, I get Vx to be 8.646 and some change, and Vy to be 27.846 and some change. How do those nodal voltages relate to our Thevenin voltage?
Vy equals VTH.
Exactly right. And lastly, how can we find I Norton?
VTH divided by RTH.
Exactly right. So that would be 27.846 volts divided by 294.515 ohms. And that should come out, I'm just going to be lazy, 94.550 milliamps. Any questions on that problem? Alrighty. So for this particular problem, we are asked to determine the Thevenin voltage, Norton current, and Thevenin resistance seen by the 3 ohm resistor here in the middle of the circuit. We're told specifically that we may assume the positive polarity terminal for the Thevenin voltage is on top and the direction of our Norton current is once again down. So which quantity do you guys care to solve for first?
Resistance again?
Okay. So when we're solving for the Thevenin resistance, we need to be looking at a dead network. So that means our 18.6 volt source is turned off. Here is our 7 ohm resistor. We take our 3 ohm resistor out because we were explicitly asked to find the equivalent circuit as seen by the 3 ohm resistor. Our 6.5 amp current source is going to be open circuited. Here's our 5 ohm resistor. Here's our 2 ohm resistor. So what resistance do we see?
They're all in parallel.
I believe that to be true, but just to double check, I'm going to identify my nodes. So I've got this red node, and then this blue node. They are all indeed in parallel. So that's going to look like 1 over 7 plus 1 over 5 plus 1 over 2, all to the negative 1 power. 70 over 59 or 1.186 ohms. Which matches what we got here. All right, so I'm going to make an executive decision here because we found Thevenin voltage. For the last problem, we're going to find the Norton current for this one. So we're going to replace our 3 ohm resistor with a short circuit. So we're going to have 18.6 volts, 7 ohm resistor, short circuit. Our Norton current is the current flowing down. Then we have our 6.5 amp source flowing down. Our 5 ohm resistor and our 2 ohm resistor. So how might we go about solving for our Norton current?
Nodal.
So
Isn't like all of the right of it short circuited?
pretty much. So
Yeah.
this 5 ohm resistor and this 2 ohm resistor are not going to contribute anything because they are in parallel with a short circuit. So the reason why I was hesitating when the student suggested nodal is because nodal involves setting up a system of equations using Kirchhoff's current law. And I think we can solve this literally just using Kirchhoff's current law, right? So what I mean by that is by inspection, the 18.6 volt source and the 7 ohm resistor are in parallel. So I can say that there is a current of 18.6 volts over 7 ohms flowing to the right. I know that there is a current of 6.5 amps flowing this way out of this node because that's the only way that that current source is going to be able to push 6.5 amps down through there when we know none of the current is going to flow to the right through that 5 and the 2. So to me, it looks like I Norton is just going to be 18.6 volts over 7 ohms minus 6.5 amps. Which I get to be negative 3.8428, so 843 amperes, and I'll be damned if that doesn't match what my expected answer was. Finding the Thevenin voltage would be as simple as saying VTH is equal to I Norton times RTH. And I'll just be lazy once again and call that negative 4.559 volts. Okay, any questions regarding the in-class assignment? Okay, so there was a question regarding one of the web work problems for the homework set involving Thevenin and Norton equivalent circuits. So give me just a moment to pull that up and then we'll take a crack at that as well. If I'm not mistaken, it was homework 9, problem 4.
Yes, sir.
So let me jump ahead. So in this particular problem, I'm going to actually, Austin, you were asking about it, right?
Yes, sir.
Okay, I'm going to use your numbers just because mine have a bunch of negative signs. I don't like it. Student progress. Austin Utley, 9, problem 4. Gross, you have more negative numbers than I did. It'll be okay. So we have a resistance of 10.5 ohms over here on the left. And then there's a current source that's drawn with a direction up. However, it's given a value of negative 6 amps. So I'm going to just put positive 6 amps direction down. Then we have a 17.5 ohm resistor. A 19.5 ohm resistor. A 17 ohm resistor. And then a 76 volt source, positive polarity on the bottom. Now, the way that this is drawn on WebWork, it effectively has, it calls them terminals, but they're drawn as if they were nodes. So I'm going to explicitly draw terminals here simply by just extending those nodes out. So this is A, this is C, this is B, and this is D. We're asked to find the Thevenin equivalent of the network seen between terminals A and B, and then between terminals C and D. And those should give us different results. I just want to be clear about that. So between A and B. So I'm going to draw things slightly differently here, okay? It's going to be incredibly similar. So here's my 10.5 ohm resistor. Here's my 6 amp source. $17.5 ohms, 19.5 ohms, 17 ohms, 76 volts. Because I'm trying to find the Thevenin equivalent with respect to terminals A and B, terminals C and D literally do not matter at all. So I'm just not going to bother drawing them. And I'm going to choose to put terminal A over here. Actually, it should be uppercase A. And terminal B down here. So these terminals are still connected to the same node. I've just drawn them in a way that looks a little bit more like we're used to. Okay. So if I want to find VTH for this, what do I do?
It'd be the voltage drop across the 10.5 ohm.
Exactly right. So if I put finding VTH, let me just make a copy of this thing. So let's just throw the positive polarity on top. And what circuit analysis technique might we use for that?
Nodal.
Sure, why not? Seems like a perfectly reasonable thing to me. So I'm going to solve this as if there were two nodes. I'm going to choose for the bottom node to be ground. I'm going to call this node X and this node Y. And so when I write my KCL at X, I'm going to have Vx over 10.5 plus 6 amps plus Vx minus Vy over 17.5 ohms is equal to 0. And then KCL at Y, I'm going to have Vy minus Vx over 17.5 plus Vy over 19.5. Excuse me, that should be ohms, not volts. Plus Vy plus 76 volts over 17 ohms. So it would be Vy minus, and then because we see the negative polarity, minus negative 76 looks like plus 76 equal to 0. Solve this system for Vx and Vy, which I'll leave up to you. And hopefully we can see that Vx is the same thing as the Thevenin voltage. Does that seem like a reasonable solution path, Austin?
Yes, sir.
Okay. So for the Thevenin resistance, it would be a similar thing. We would just turn off the sources and all of that kind of stuff. So to me, that would look like 10.5 in parallel with 17.5 in series with 17 in parallel with 19.5. Just simple resistance combination. Just for the sake of showing you how to redraw things, let's look at how I would redraw for C and D to find the Thevenin equivalent between C and D. And I'll leave it up to you to do all of the calculations and stuff. So between C and D, we have that resistance of, 10.5 ohms here. We still have a 6 amp source here. Seventeen and a half here. $19.5 here. And then I'm going to squeeze the resistor R4 and the voltage source like so. And the reason why I squeeze those things down is because this node right here is node C. And so that's going to allow me to just extend this and put a terminal over here, extend this guy and put a terminal over here. And now it looks like what I'm used to dealing with. And it would be the exact same process. Our Thevenin voltage would just be the drop across this set of terminals. And we could do that using nodal analysis, mesh analysis, whatever we particularly felt like, and all that kind of good stuff. Did that explain the question that you were posing in your email?
Yes, sir. I was just wondering how you would draw that because they had it identified as like a node, and I was like, how do you chop that off?
Yeah. So the short answer is you just redraw it to make it look like you could extend it. Like there's nothing stopping me. Let me scroll back up here from literally just analyzing this thing where I just extended each of those terminals out to make them look like terminals. But it looks slightly different than I'm used to. And so that's why I redrew it again to make it look like something more in line with the way that I teach it. All right. Does anybody have any questions or comments about really anything at this point?
What happens if you multiply VTH and INO?
You're going to get a number in watts. I don't think it necessarily means anything, but
Okay, I didn't know if that was something.
I'm not aware that that is a quantity that we are interested in for any reason. Yeah, so nothing stopping you from multiplying them, but I don't think it gives us anything useful. All right. Well, I hope you guys have a great rest of your afternoon, and I will see you on Wednesday to continue our discussion on Thevenin and Norton equivalent circuits. We're going to add dependent sources in and kind of see how that messes with things, and then how we can correct for that. So see you guys on Wednesday.